Box plots are a method in stats where we can represent or visualize a spread of data in a diagram. Now, for such a diagram, you are going to need 5 values. From the data set, you are going to need the minimum value, that is to say the smallest number, the lower quartile, that which is a quarter of the way through the data if you were to line them up smallest to largest, the median, that should be in the middle of the data when arranged from smallest to largest, upper quartile, which is 3/4 of the way through, and then the maximum, which is the highest value. What you would then do with these numbers, if we were to just, let's say the minimum was 0, lower quartile was 2, median was 5, upper quartile was 7, and the maximum was 10. You would put 5 vertical lines above this line or axis you have at the bottom. There's no y-axis, just an x-axis. And they're not really supposed to touch the x-axis. It's just going to be some way above the axis and as best you can about the same height. So at 0, at 2, at 5, at 7, and at 10. What you will then do is join up the tops and bottoms of the middle 3 lines to form the box of the box plot, and then you'll draw whiskers going out to the sides here. Now, from this we can see the average, which would be the median, but we can also try to gauge the interquartile range. Now, the interquartile range, or IQR, is a measure of consistency. So the lower the interquartile range, the more consistent the data. The higher the interquartile range, the less consistent. With this in mind, one other thing we could just mention, just from the fundamental standpoint, is this idea of an outlier. Let's say that we had a point out here. Now, usually this line on the right would be the maximum, therefore you couldn't have anything further to the right than it. However, with outliers, what we're going to say is that if you are either above the upper quartile plus the interquartile range, or less than the lower quartile plus the interquartile range, then you are an outlier. You are too far away from the majority of the data to be considered you are an anomaly. So if we would say 11 was actually in this data set, and yet this 11 fell beyond the outlier boundary, the arm stops at the boundary, and that piece of data afterwards is simply represented by a cross. Because we do want to acknowledge that it exists, it is part of the data, we also need to give some indication that it's an anomaly. With that in mind, let's just give an example of how we could get such values from a data set and then apply them to a diagram. We have here just on the right 15 numbers, so 3, 1, 2, 3, 9, 1, 5, 6, 5, 7, 4, 9, 5, 8, and 9. In order to get the minimum and the maximum, well, we can just see here, the smallest value is the 1, and the maximum value is 9. But as for the quartiles and the median, we're going to need to put these in order. So, putting these in order, we would have 1, 1, and you may want to just like acknowledge them in some way once you've done them so you don't double count. Then 2, 3, 3, 4, 5, 5, 5, 6, 7, 8, and then 9, 9, 9. From here, what we can do is try to find the median. In this case, since there are 15 numbers, it's an odd number. What we can do is if we add 1 to that total, so 15 add 1 is 16, and then divide that by 2, 8. 8 is going to be the middle number, or the 8th number. So 1, 2, 3, 4, 5, 6, 7, 8. And you just want to verify, so we've got 7 numbers to the left of it, and 7 numbers to the right of it. It is indeed in the middle. If this was on your paper, what you could also do is kind of count inwards. So take off the 1, take off the 9, take off the 1, take off the 9, 2, 9, 3, 8, and so on, and work inwards until you find this middle number. So in this case here, our median is going to be 5. Then for the quartiles, if you now were just to look at what's on the left of the median, so from this 1 to this 5 here, we have 1, 2, 3, 4, 5, 6, 7. Well, the median of the 7 add 1 is 8, and half of 8 is 4. So 1, 2, 3, 4, going to get a 3, and just to double check, 1, 2, 3, 1, 2, 3. Yep, there's 5 on either side, remembering we're going to just before the median. If you then do the exact same thing on the right-hand side with that 7, so that will be the 4th digit in. So in this case, that's going to be 8. You've got the 1, 2, 3, 1, 2, 3 on either side. Now that we have these numbers, we can plot them onto here. So our minimum is that 1, and the lower quartile is the 3, median the 5, upper quartile is the 8, and the maximum is the 9. So we then draw up the lines on top of the bottom of the middle 3 to make the box, and then draw the whiskers here. Now in this case we were very unlikely to get any outliers, as we just went straight into drawing the box plot, but officially if we were to check the interquartile range for this data would equal the 8 minus the 3. So yes, the interquartile range is the difference in the quartiles, upper minus lower. So interquartile range is here going to be 5. So for the lower boundary, if we do our Q1, our lower quartile, 3 minus 5 would be minus 2. Yep, no one's down there. And then for the upper boundary, this 8 add 5, that would be 13. Yep, no one's up there. So we indeed don't have any outliers in this data set. This is just what the box plot would look like. That, for box plots, is most of the concepts. We're going to get on to comparing data just a little bit towards the end, but for now, if we're happy with just how we can get these 5 values from a data set, check for outliers, so get your interquartile range, the upper quartile minus the lower quartile, and then either add it to the upper quartile or take it away from the lower quartile and see if there's any numbers that are beyond those values. Once you have those, plot on the box plot, and hey presto, you have it. If that's all fine, let's just see how you get along with an example of your own. So, you have these 20 numbers here. And we're to find the median and the interquartile range, then draw a box plot indicating any outliers, and then finally find the mean of this data. Mean hasn't been mentioned so far because it's not traditionally part of a box plot question, but we can still use it when working it out for a general data set. So, pause the video, have a go for yourself, and then press play again when you're ready to compare. First of all, if we're going to be finding the median and interquartile range, we indeed need to put these numbers in order. So, the smallest are the 14s, so we have 14, 14, 14. Then we'll move on to the 15. So we're going to have 1, 2, 3, 4, 5, 6 15s. So 1, 2, 3, 4, 5, then 6. Onto the 16s. Once again, we're going to have 6. So 1, 2, 3, 4, 5, 6. 17s, you're going to have 1, 2, 3. So 1, 2, 3. And then the last two we haven't done, the 18 and the 25. Okay. Now that we've got them in order, we can find that median and interquartile range. Now this time we have an even number here, whereas before it was odd, so there was actually a number exactly in the middle. Here, the middle is going to be between the 10th and the 11th number. If you want, you can do the thing before of adding 1 to the total and dividing that by 2. So 20 add 1 is 21, and half of that is 10.5. If we were to look at like whatever was here, you'd end up with these 10 digits on the left, and well, 10 numbers on the left and 10 numbers on the right. Now, as it happens in this case, the numbers on either side of this midway point are both 16. So you can just take your median as that 16. If they had been separate numbers, then let's say it had lain here between the 15 and the 16, then you would have taken 15.5, or in general, it's whatever is halfway between those two numbers. Once we have this, we're then going to have to do the same thing for the quartiles. So here, because we have 10 numbers, halfway for that is going to be between the 5th and the 6th digit. So 1, 2, 3, 4, 5. So that's going to be here. We've got 5 here, 5 here. Once again, that's the same number on either side. So our lower quartile, we will just read off as that 15. But then here in the upper quartile, this is between two separate numbers. Our upper quartile, therefore, is going to be 16.5. From these, we can then get your interquartile range, that then being 1.5, because that's the difference between the lower quartile and the upper quartile. And now that we have this, not only have we just completed the first part of the question, but we can also now work out if there are any outliers and draw the box plot. For the outliers, we're going to be using the same formulas as before. So if we're going to look at the upper quartile, the 16.5, then add the interquartile range. In our case, that's the 1.5. So that would be 18 here, or it will be the lower quartile, the 15 minus 1.5. In this case, that's going to be your 13.5. We don't get down to 13.5 on the lower end, so there's no lower outliers. However, here, this 18 here, therefore, because they're the same number, that is right on the boundary. That just gets in. But, perhaps not surprisingly, the 25 is an outlier. It's far away from the rest of the data. So, when we come to draw this then, if we just get scale, we want to be going between 14 and 25, but also we're going to have a 0.5 in there. So let's actually go up in halves, essentially. So 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, extend the line a little, 24, 25. Okay, now we'll just label the even numbers just so we have something that's more easy to reference to. And now we can start plotting. So your minimum value is that 14. Your lower quartile we have as the 15, median the 16, upper quartile the 16.5. Then the upper boundary is going to be that 18, and then we'll put a star at 25 for being an outlier. Here then, we'll just join up the box and add the whiskers. As we can see from here, this is definitely an outlier. You wouldn't have wanted to extend this arm all the way over here. And then lastly, find the mean of this data. Well, to work out a mean, you just add up all the numbers that you have and then divide by how many there are. When you add this up, you should get 322. And if you divide that by how many there are, that being 20, you get a mean of 16.1, which we can see is actually very close to the median. So that kind of ballpark, that area, should indeed be the average that we're likely to be looking at. Okay, if we're good with that, let's just see one other question. This from a paper. So the children from two schools, A and B, took part in a competition to complete a puzzle. The distribution of times taken to the nearest minute by children in school A are shown in the box plot below. And first of all, write the time by which 75% of the children in school A had completed the puzzle. Well, if we're looking for 75% of them having done it, so they're going to be 75% of people below this value. 75% is 3/4. And the 3/4 mark is the upper quartile, so this right-hand side of the box here. So if we just read that down, on this scale, because to go from 15 to 20 in 10 boxes, every 2 little boxes must be 1. That makes this here 17 minutes, that 3/4 of them were below. Then, state what the two crosses represent in the box plot above. Interpret them in this context. Well, so first of all, they are outliers. But in general, in this context, They are two people who took a lot longer than everyone else to complete the puzzle. Their times were anomalous. They didn't fit within the majority of the spread of data. Then we have that for school B, the shortest time taken was 6 minutes, the longest time taken was 22, and the quartiles were 12, 15, and 17 respectively. So yes, you may sometimes see the median referred to as like a middle quartile. Determine if there are any outliers. So for this, we need to do our upper quartile minus the interquartile range, plus the interquartile range, and then lower quartile minus it. So for the upper one, we'll have that 17 plus, and the difference is going to be 17 minus 12, which would be 5. So 17 plus 5 is 22. That 22 is just on the boundary, but we're counting it as in. And then for the lower one, you'll have your 12 minus the 17 minus 12, so 12 minus the 5 to give us 7. This 6 is below that 7. There is someone who completed it in such a fast time that they were an anomaly. Now that we've identified that the 6 is an anomaly, or it's an outlier, we can plot the box plot. So for our maximum, we're going to go with that 22. Once again, every 2 little squares is going to represent 1. So this 22 is going to be here. The 17 will be here. The median, 15, will be here. Lower quartile at 12 will be here. And then the lower boundary will be at 7, with then our outlier at 6 being here. Join up the 2 boxes and then give the whiskers as such. And lastly, now that we have 2 data sets, 2 box plots, we can compare them, compare the distributions. Now in general in stats, if you're going to be comparing 2 sets of data, there's 2 things particularly that you can talk about. You can talk about the median and you can talk about the interquartile range. So the median is telling you who was higher or lower on average, and the interquartile range is saying who was more or less consistent. And as said above, the lower your interquartile range, basically the narrower the box, the more consistent your data was, the higher the interquartile range, the less consistent. So in this case, we can say that students of school B took longer on average because their median is slightly higher. Of course, you could say it the other way, and you could say that A were quicker on average. But you can then say that school B were more consistent. Their range, interquartile range here, is going to be 5. But up here, if we read this, we'll find that their lower quartile is at 11. So even though their upper quartile is the exact same at 17, they have an interquartile range of 6, which is slightly higher, meaning theirs was slightly less consistent. Or again, we'll just stick with the B framing. So B's times were more consistent. You can also specify that it's only slightly longer, like it's only a minute longer, or it was, when we say slightly more consistent, it's actually just a difference of 1. But the main thing is you are interpreting your median. In this case, because it's time, the higher the median, they took longer on average, and then the narrower the box, the more consistent their times were.